In this lecture, we shall solve some problems on work and energy, and as this symbol notifies, the problems are chosen mainly from various competitive examination papers of repute. So let us move on to the first problem in the lecture, that is telling us a string with one end fixed to a rigid wall passing over a fixed frictionless pulley at a distance 2 meters from the wall has a point mass capital M is equal to 2 kg attached to it at a distance 1 meter from the wall. Another mass small m is equal to 0.5 kg attached to the free end is held at rest so that the string is horizontal between the wall and the pulley and vertical beyond the pulley. We shall introduce the figure shortly. What will be the speed with which the mass capital M will hit the wall when the mass small m is released? And the figure given is this one. As you can see, this is a rigid fixed wall, vertical wall, and this is a fixed pulley. And there is a large mass, point mass capital M, that is attached to this horizontal part of the string. Initially, this M is given to be 2 kg. I'm writing it here. And another mass, small m, is attached to the free end of the string, and this mass is given to be 0.5 kg. Initially, this block is held with hand so that this portion remains vertical and this portion remains horizontal. Remember, this pulley is a fixed one, and the point at which the string is attached to this wall is also a fixed point. I'll be taking for convenience this point to be the point O and the pulley position to be the point P. The initial position of larger mass, that to be capital A, and initial position of the smaller mass, that to be point B. And they have given the data also regarding the length of the horizontal part of the string. We have been told that the length OP, this is 2 meters, and the larger mass capital M is held at the midway of this OP, that is the length OA. This length is equal to 1 meter. The question is, once this block small m is released, you can make out that larger mass capital M is on the left hand side. Therefore, it starts moving down, but not vertically. Since this is attached to this point O with a string that is assumed to be taut, this large mass capital M can only move in a circle in a vertical plane of a fixed radius equal to this 1 meter, and eventually in a circular path it hits the wall at a point. And as this capital M, this large mass, is going down in a vertical circle, it's obvious that the smaller mass is also going up vertically along this line BP. The question is, at what speed does the larger mass hit the wall? And we shall solve the problem by applying the principle of conservation of mechanical energy. Let us see how we can proceed with that. So this was the initial position of the blocks before the smaller mass was released. And I'm going to draw now one more figure side by side to see the situation, the positions of the blocks at the instant of the larger mass hitting the wall. And it's important to draw these two figures side by side at the same level so that we can understand the difference in height of the blocks after the block M was released. Therefore, I draw an imaginary line to the bottom of this rigid wall and introduce my second figure. As you can understand, this is the point of attachment O that remains fixed. This is the pulley that's also fixed. And initially, my two blocks, they were at the positions A and B respectively, isn't it? Initially, it's here, the larger block in red color, and this is the position B of the smaller block in blue color. I have already said after this block small m is released, the larger mass is falling in a circle in a vertical plane of radius equal to 1 meter and hitting the wall at a point. Therefore, if I might show the path of this red block, this is moving in this circular path in a vertical plane, and eventually this is hitting the wall at this position that I am calling it to be position A dash, say. And as you can make out, the length AP has now become much larger because the string has to be with this if the string has come so much from the point A to the point A dash, it's obvious this length A dash P is much larger than the length AP, and therefore this length PB also has decreased. In other words, the block M that was initially here has come up to this new position that I'll be calling it B dash, isn't it? And both these blocks possess velocities at the instant of hitting the wall. This larger mass, capital M, its velocity vector is pointing along the tangent to the circle, which in my figure happens to be in the leftward direction. Let me call this velocity to be V. And at the same time, the block small m is going up at the position B dash, and its velocity at this point is taken to be V dash, say. You have to understand one thing at this point, that although the V and V dash, they are different velocities because of different directions, but since the string is taken to be inextensible, the constrained motion of the two blocks implies that the linear speed of both the blocks, capital M and small m, have to be the same. That's very important. Directions are different, but the linear speeds of both the blocks are the same at the instant the larger mass is hitting this wall. So I might write down here, to avoid any ambiguity, that the velocity vector V and V dash, they have the same magnitude V at the instant of larger mass striking the wall. This is the capital M, larger mass, and this is the smaller mass, small m.
Hello students, you got a glimpse of our video lessons through this small lecture. We have hundreds of lectures like this one, covering various topics of advanced school level and intermediate physics in our website. They are exhaustive and often accompanied by elaborate diagrams to make concepts even clearer. They are taught with passion and sometimes with a bit of fun. So, at the end of the lesson, you have a commanding grip on the subject and you are ready for the board and competitive exams. Subscribe at physicsacademyonline.com to access video lectures of highest standard on various topics of physics.